Can everyone see this?
Yeah.
Okay, so each of you have a remote login using remote desktop. And each of you use a specific port number along with this IP address when you start remote desktop. So if we open up remote desktop, what you're going to do is use this first IP address and then a colon and then a specific port number. I'm going to read the port number that you're using for your own server. You have a server 2019 standard edition virtual machine. And the password, the login you'll use, you're going to use a login that uses in all caps Groovy. And then you're going to put in your first initial and last name. So if it were Luke, he would put in Groovy /L Bullock, and then he'd have his own port number. And I'm going to give that to you separately. But each of you know the last 4 digits of your own student ID, right? So what you're going to do after you enter the first initial and last name for your login, you're going to use capital R EM0TE dash, and then the last 4 of your student ID. Does everyone understand what we're saying?
Yeah, I understand. Yeah.
Okay, so what we're going to do now is practice access. I'm going to provide your port number by audio. I'm not going to share the screen because I have a listing, but I'm going to tell you what your port number is. And each of you know your own student, the last 4 of your own student ID. So I'm going to go ahead and minimize this, stop sharing for just a moment, stop recording for just a moment. All right, can everyone see my screen?
Yes.
Yes.
So each of you have a server assigned. We are going to repurpose the 2 servers that Shanoa and Deanna used, which was Virgo and Pegasus. Okay. And if I open up this window, I can show you right now on Virgo, I'm logged in as Deanna. So basically, what I need to do is log you out and then let you try to log in. So that's what I'm going to do. But this is, I just logged in with that password, and I wanted to show you that you do have a successful login and it works. By the same token, here's Pegasus, right? So if you look at Pegasus, Shanoa's logged in. And if I look at Gemini, I think is Luke. Yeah. So what I'll do is I'll go ahead and enter your password one more time and then sign out. And I'd like to stop sharing and then have you share your screen, and then let's walk through the connection together, okay? So here we go.
Yeah, we can see.
So as we concluded our last session on disk preparation, we were talking about the different partition types. There were two different kinds of partition types, partition table types. One was old school, and one was newer that allowed for larger size. Can anyone recall what the two different partition types were, or one of the two different types? When I went to initialize the VHD, it said, hey, you have to choose one of these two partition types. Does anyone recall?
You mean like at TFS then?
Well, that would be the type of file system. So we'll be getting into the type of file system shortly. One type was MBR. So main boot record as opposed to, or master boot record. And GUID, GUID, right? So it's a GPT, and the G stands for GUID. So it allows for much larger volumes. Just remember that if you want very large disks, you got to use GPT, that there is a size limitation for MBR. And that's something I want to call out intentionally because that causes a lot of issues, especially now with such large disks, right? So the first thing you do is you initialize a disk, then you partition a disk, and then you format a disk. When you're formatting the disk, you're taking the outside boundaries of the sports field. So if we're using the analogy of the, a farmer selling his land and a developer setting up a sports complex, when you partition, you're creating the outer boundaries for the baseball diamond, the soccer field, the football field, and so on. When you format the disk, that's just like putting down the yard lines, the hash marks, so that there's an index, a logical index for the data storage. And there's basically a physical, just as memory management includes physical memory frames versus logical memory pages, there is a physical index, right? So we'd call those disk sectors. And then on top of the physical disk sectors, you have a logical index, which you would call in the Linux world or in the Mac world, inodes. And in the world of Windows, you would call it an allocation unit. So in Linux, the logical index that's overlaid on top of the physical marks that are made on the physical hard disk would be disk sectors. And then you'd have inodes in Linux, or you'd have allocation units in Windows. We said before that the size of the allocation unit can make a big difference. So in Linux, the default size for an inode is 1 kilobyte or 1024 bytes. In Windows, it's 4096 bytes or 4 kilobytes. That's the default size. But if you're using a disk, especially a disk for a physical hard disk for virtual hard disks, you should always use the very largest data files available. And that's because, or if you're using very large database files, you're doing a lot of streaming media with very large video or media files. Whenever you format with a much larger inode size or an allocation unit, what happens is that it loads a lot more quickly. It's kind of like, do you want to move furniture with a Toyota Yaris or an 18-wheeler? So when you use the largest format the logical index, when you format and prepare the drive to store data, you want to be sure that depending on its use and the case that it's used for, that you use an appropriate size. And especially with large data files, you want to use the larger inode or allocation unit. Now, there is a trade-off when you do this. You can have a very large allocation unit or inode size, and if there are smaller data files, only one data file can be stored in a given inode or allocation unit. So if you have a 2 megabyte, let's say that you maximize this and you say, okay, I'm going to use a disk for the creation of virtual hard disks, and I want them to load very quickly. So you choose, when you're formatting, instead of 4096, you choose an allocation unit size of 2 megabytes. And then you have a 1K text file. When you're wasting 1.99999 megabytes of disk space, because the 1K space, the rest of that's going to be called slack space. The other thing that can happen too is that if you use smaller sizes, because you want to be more efficient with smaller data files, the incidence of fragmentation tends to be much greater, okay? The important thing is to give some thought to the size, and this rarely happens. So I just want to put that out there. When you are developing applications and solutions, you should specify for the people as a matter of supporting documentation. Here's the installation guide for your enterprise solution, right? So when you get into software engineering, if you haven't had the software engineering class yet, you're working with teams of people, you're developing a enterprise solution that everybody uses, and everybody's complaining about how slow it is, how inefficient it is. A lot of that can be very practical. It can be a very practical situation where the solution developers didn't think about the file system dynamic, right? They didn't consider that, okay, for this enterprise solution, we're using a lot of media files. We need a very large. So that's, again, you want to put that in supporting documentation and installation guide. And you want your technical people to prepare a disk properly for the type of data that's being stored on it. And that will make a huge difference in terms of wasted space or disk read writes overhead with fragmentation, because it's just reading and writing and reading and writing too much. And it's a condition that's very much similar, like thrashing, only it's worse, right? The more slack space you have, it is an ideal place to store malware. So one of the things you want to consider is that depending on the environment, if it's a high security environment, you absolutely would like to do that. Ideally, this convention of formatting and indexing a disk with uniform data sectors, logical data sectors, that's been around since the very beginning. And nobody's ever really thought of, redesigning a component of an operating system so that there are custom sizes for data storage, and that would be a significant innovation. So if you're ever thinking about developing operating systems and working innovations for an operating system, our course is about operating system principles, right? Nobody's ever really devised a setup for disk I/O and file systems where, the horsepower that we have under the hood in terms of hardware now could easily do this. You could come up with a simple algorithm that basically says, okay, if I have a very large file, I'm going to create logical index logical index references on the fly, so I can size them as I'm storing the data, and I won't have any fragmentation, right? I won't have any slack space. You would dramatically increase the efficiency and the security of disk storage, because there wouldn't be any spare space for people to store stuff, and there wouldn't be any fragmentation, right? It would just find the allocation unit, right? They would find the allocation unit in a Windows disk, or they'd find the inode on a Mac or a Linux system, and they just perform one read operation on that. And if you think about a drive head hopping back and forth to try to find stuff, that's a pretty crazy environment, right? Any questions about sizing and application considerations? Just remember, if you have a lot of log files, a lot of smaller text files, a lot of smaller data files, you do want to use a smaller inode or AU allocation unit, right? Okay. So we have a special topic about RAID. We've already covered RAID as far as disks. Network attached storage, host attached storage, and cloud attached storage. Those details are embedded in the RAID, the extra RAID document, the special topics document. Direct attached storage is the same as host attached storage. So if you see DAS or HAS, it's the same thing. It means that the disk array, the storage component, the disk array is connected directly, right? So here you have additional information about each of those things. There's a quick YouTube video about network attached storage and how it's different. Just remember, it's file level access instead of disk level access, right? So you have to work through an operating system to get at the information that's stored on a NAS across the network. In a SAN, you do not have to. The network connection appears to be just like any other disk that's sitting on your system. It's a hardware level, disk level access. So it looks like a raw hard disk, right? We said SCSI was, it stands for Small Systems Computing Interface, right? That convention has been around an awful long time, and there are different, in the older days, legacy systems have parallel ATA instead of serial ATA. You may have heard the term SATA. These are some review aspects of the computer architecture course. So you have serial attached storage, and the first interface was called IDE, and now you have serial attached SCSI. So it used to be parallel in nature. They found a way to do it in series. So the disk media still has to be prepared first before use. That's called initialization. So that's something that's really important. There is a weird sort of wrinkle that occurs for NAS versus SAN. There are some cases where if you're using virtual machines and you store the virtual machine in a SAN and it has to load a large VHD, you can get bottlenecks because on the disk level, you can't load. Only one person at a time can access the file one at a time. So when people are accessing a SAN store across the network, it's a one person at a time kind of thing. With NAS, it's an older technology, and multiple people can download or read they can transfer the data from a NAS store simultaneously. So if you have a classroom where 20 students need to load up a VHD, you want to work with NAS instead of SAN. This is one of those little ironies where it's like, okay, SAN is a much more advanced, much higher performance technology. It's much newer, but in certain scenarios, the traditional NAS actually works a lot better. So here's more detail about network attached storage, how old it is. A Stanford University alumni named Scott McNealy, who was an early rival of Bill Gates in 1982, came up with this network file system, right? So the idea is that we're going to take a file system and we're going to extend it into the network. So the network is the computer. And that was Sun Microsystems' tagline. It was like, the network is the computer. They were trying to pitch the idea that a local machine was limited. Why would you do that? Use our Sun Microsystem. Don't use Microsoft, because all you have is one computer and a local disk. If you're using Sun, you have an entire network of network disks. And so there were two specific file systems that were specialized for accessing or extending the file system across a network environment. And that's a pretty big development. So that's where distributed file systems and distributed computing systems becomes a reality. So that concept has been around for a while, but making it affordable and effective hasn't been around for so long. Just in the last 10 years, there have been tremendous advancements, and now everybody's talking about the cloud. So this is sort of like an early version of the cloud. And that's one way to look at NAS, and in particular, NFS. So NFS is running as a service on a server. What you have is basically a file system that you can extend across a local area network or even a wide area network, right? So after a time, computer engineers realized that network disks, the design could be improved. Then you get to the notion about a SAN, okay? So a SAN can be considered like direct attached storage because it presents block level access to the disk directly. So not file level access, but block level or disk sector level access to storage. So instead of sharing a drive, they had this phenomenon where you'd have a network drive or a network mapped data store with NAS and NFS. And when SAN came along, it was like having a network drive on steroids or a LAN disk on steroids. So if you hear the term LAN disk, that's tends to be a general reference to like a network store, a network share, a drive map. There are all these different terms that are used to talk about network-based storage. But when you get to block level access, because of the technology and because of the performance of the hardware associated with block level disk access, you really have the equivalent of a local disk. And then you can work with diskless servers and then have just a huge array where you can spin up or down dozens or hundreds of servers. If you've ever wondered, okay, how does Amazon Web Services make it possible for you to just load a server, just create one, and there you go, and it's ready to go in just a matter of seconds? That happens because of SANs and iSCSI and all that, right? In short order. Cloud attached storage is a royal pain in the neck. So this idea of cloud attached storage, Microsoft wants everybody to store their stuff in the cloud. That's because they want everybody to pay a license fee every year to renew their Office 365 subscription. And what they're doing is embedding hooks in the operating system so that when you open up File Explorer, there are actually links embedded in your File Explorer for OneDrive. OneDrive will appear if that's turned on. Now, I have disabled OneDrive so that it does not load. I've reconfigured mine. I don't want OneDrive active. That's because I put a lot of things in my documents folder. And I don't want my user profile stored in the cloud because I don't always have a cloud connection. But it goes without saying that, you know, cloud connections are very dependent on the speed of your internet. And so one of the things to remember about performance considerations and storage types is that for the best performance with an application and with an operating system, a file system and an operating system, you want direct attached storage. It is 1,000 times faster than network local disks, okay? Network disks are 1,000 times, generally speaking, there's, you know, a significant decrease in performance. Then when you go from there to the cloud is 1,000 times worse than local network stores. So the cloud is 1,000 times slower than NAS or SAN. And that's huge. So when you're at a point where you're not using a local server directly, you're working it across a local network, that's 1,000 times slower. And then when you go out to the cloud, it's 1,000 times slower than a local network store. So if you develop an enterprise solution and it depends on cloud attached storage, you really have to watch how much data is flowing. Might be better to have certain solution components running on a local server with just the data traversing the cloud because of those considerations. Are there any questions about performance considerations for the different levels of network storage and file system storage? Everybody wants to go in the cloud. They all think it's cheaper and quicker and easier, and it's not. There are trade-offs, and the performance dynamic can be a killer. So don't drink the Kool-Aid when you arrive in your first when you arrive at your first job sites after you graduate. I would recommend that your first response to somebody who says, yeah, we're putting everything in the cloud, you could say, well, you realize there are trade-offs. We should probably benchmark those. We should probably test those because the performance considerations could be very serious, right? Does anyone have any questions at this point? Anyone? You still with me? Shanoa, Luke?
Yeah, I just don't have no question.
Okay. So one of the things we want to talk about for file systems, file system efficiency depends on the type of disk scheduling algorithms that are working on the back end. When you're dealing with, doesn't matter which file system you're talking about, the algorithms underneath the hood. So you have these different, and I'm using a different reference here. So I'm dipping back into an online reference that, let's see if this should still pull. The open source textbook that we used to use. This is a free reference online. And so there are quick references that talk about how the operating system provides algorithms to enhance disk access. And there are different types, right? So they talk about the different scenarios, a simple disk drive, how you might have multiple tracks, so the heads have to rotate and move. There's more explanation about how the physical aspects of the disk actually operate. That's good. It's good information to know. So the finer points of disk I/O, if you've ever wondered how the disk head reads data, you have different spindles or concentric circles in the tracks, and the ones and zeros are arranged in successive disk sectors. And so that's how a disk is organized for traditional hard disks. All of that goes away when you're dealing with a solid state disk, right? So in any case, the takeaway from this chapter and this online link is that it also gets into the different algorithms. First come, first served. There are specific, yeah. So there's an algorithm known as SSTF, right? So if you basically know the simple acronyms, you're good to go. You'll see that information in the study guide and addendum, right? Shortest seek first, SS. Shortest seek time first, as opposed to shortest seek first. So you have SSTF versus SSF. Nearest block first, right? So you have all these different algorithms that are developed. There is one concept I think that's really important to understand on a basic level, the elevator algorithm. So an elevator, how many of you have ever ridden an elevator? Everybody here has been on an elevator, correct?
Yeah.
Okay. So I have a question to ask you. If you get into an elevator at the bottom floor, and let's say you're going to the 8th floor, if you press the button for the 8th floor, do you automatically go directly to the 8th floor without a stop? What usually happens? What usually happens in an elevator?
If people on a floor lower than 8 press the button to go in the elevator, then it's gonna stop.
Exactly. It's going to stop along the way, right? So what it's doing is it's making a single pass between the floors. And if you're talking about a hard disk, we'd call that a sweep. That's like going from the ground floor to the 8th floor, and you're making a single pass, but then you're stopping along the way, right? So SCAN or C-scan, right? Scan or C-scan is a version of the elevator algorithm, and they've made some improvements, but basically, just like a lot of the algorithms that have been developed, there are trade-offs. The important thing to understand is that because of the physical nature of the disk, where it's spinning around, it's you depending on the nature of the operating system and the kind of data that you're storing and the level of fragmentation, it gets to be pretty complex. So there's a lot of things that we take for granted when we're accessing a hard disk. The simple truth is, one of the most common conventions is this idea of an elevator where, in order to be efficient, it's reading and writing different sectors for different purposes while this thing is spinning. And it's that elevator algorithm. So in some operating systems where a specific type of data and computation is a primary consideration, you might have an operating system that accesses disks with the shortest seek time first, or the nearest block first. it's important to understand that based on the computing scenario, the selection of disk access algorithm can help a person who's working an operating system component as a part of an enterprise solution. They can gain significant efficiencies by using one as opposed to the other. And so that's the whole intent of examining the different styles. So the author does a pretty good so which one is fastest, or which one is best, or which disk sector gets access next, right? So which should it serve next? And so the author says, well, the answer is, of course, it depends, right? It depends on the scenario and the trade-offs. So you've heard me say that repeatedly, but that is the reality. I'm not just telling you that. Well, it depends, and it's not a cop-out. Depends on the scenario and what's happening with your application and the context. The context is everything. So please take a little bit of time to examine each of those different disk methods and the basics about them from the reference. Any questions about the different types of disk access references, the disk access algorithms we've just taken a glimpse of?
No questions, but I do want to let you know that Deanna told me to tell you that she's just having connection issues. She's been trying to reconnect, but she's having issues.
I understand. Thank you. So yeah, there is another handy reference to look at. This one about drives is really comprehensive. So this particular disk IO reference, the link on the bottom, there's a lot of really decent information here, and so I just thought that I'd call out this resource in particular. You would want to spend some time in review, because some very basic sensible concepts, right? So we talk about caching and the memory hierarchy. That was something out of computer architecture. The closer you are to the CPU, the more expensive the memory. You have SRAM cache level 1. It's sitting right next to the registers and the controller, the arithmetic logic unit. The further away from there you get, the larger the memory capacity is, but the slower it is to access, and the less expensive it is per megabyte or per gigabyte, right? So this is just a very good recap of some of the aspects that we're dealing with in terms of how disks read and what they do. And it's very, very well written for an open source reference. And so that's why it's linked in on your study guide. So there is a special topic when you distinguish between Linux disks, partitions, and volumes. It is you should see it in the special topics section, and it's called Linux versus Windows. So I just thought we'd take a quick look at this. You may already know some of this. The root of a logical volume in Windows is provisioned using a drive letter. It's a throwback to the disk operating system days when IBM and Microsoft sold computer systems that had floppy disks, right? In a Linux system, we don't have drive letters. It's just a / that represents the root of the file system. That is not to be confused with the root account, that's the administrative initial account created when the operating system is installed, right? So root and root are two different things. Yeah, and sometimes that's a crazy point of confusion. When you're joining an Active Directory domain, it embeds the domain admin's universal security group into the administrators group on the local system. This is not quite like inheritance on the file or share level, but similar. So we'll talk about permissions, privileges, and inheritance in just a minute. But essentially, if I look at my own PC and I look at computer management here, inside my system, I have certain groups, and there's an administrators group. And this is how root privileges are provisioned to specific accounts. And typically when you install the operating system, one of the default accounts that's set up is literally called administrator, and it's in the administrators group. When a computer, if my computer were to join, like if I look at the name of my computer right now, and I look at my system properties and go to about, the name of my device is ThinkPad, but it's part of a standalone security account management context. So it's a standalone security model. When I join a domain, right now I'm in a work group called VI SERP, which is it's an education interest from the College of Science and Math at UVI, and I'm sitting on a UVI laptop right now. So we created a work group called VI_SERP, which has to do with education and research with K-12 schools. So we'd have summer programs for K-12 teachers where we do STEM activities and really cool stuff. Anyway, make a long story short, there's a work group called VI SERP, and the name of my computer is ThinkPad1. Now, if I join a domain, I can extend the file system effectively across the domain. And the thinking about that is kind of counterintuitive, but essentially what happens is that in a domain environment, the computer now belongs to a domain that's a member of the domain, just as your login account is a security account that belongs to the domain. So there are computer accounts and user accounts. And so this becomes a method of extending the operating system. Now, especially the file system. Inside the administrators group, if I were to join the groovy.local domain, so each of your servers are a member of the groovy.local domain. And because they're a part of that domain, each of your servers has a member account in the domain. Why don't I just show you? So let's do that. Can everybody still see my screen?
Yeah, we can still see it.
Okay. So if I look at my domain controller, what you see is the basic structure of the groovy.local domain. This is an Active Directory domain that's created on a host known as Rigel. And Alnitak and Sirius are the two domain controllers for that domain. And so I have some objects in the domain. So in the Active Directory schema, we have these objects that are called organizational units. And I can create an organizational unit that's a container for the St. Thomas OEK campus and a logical container for the STX Albert A. Sheen campus. And you'll notice that each of you have your user accounts in each respective organizational unit. Everybody with me so far? So Luke and Shanoa are both on the Albert A. Sheen campus, and their servers also have an account, a computer account or a system account. And those computer accounts are also stored in the same organizational unit. Now, I've created this convention. I thought it would be good to have a way to control the security and features of the user and system accounts based on campus, based on location, right? But you can also create sites for a given domain and then control aspects of the operating system and the file system across the domain using something called group policy. So I can basically delegate control, I can create policy, and then I can link that policy to given organizational units. And that's one way I can control every aspect of the system or user accounts and the data from a central location. So what I'm doing is taking the idea of a disk and file system that would control a local operating system, and I'm providing a context to extend that across an entire organization, across different geographic locations and sites, right? Or across different organizational components. So we could have a student's organizational unit, a UVI staff organizational unit, and we could have a faculty organizational unit. And I can delegate control of that to a lead member of faculty or a lead member of staff or a lead student in each class. But once we join the domain, the computer account appears here and I have to transfer it into one of these organizational units. So when I join a domain with my computer, I could, what do we mean by join a domain? On my local laptop, when I go to, let's see, where was I? Here, on my local laptop, I'm a member of a work group, but I can change this. And instead of being a member of a standalone security model in a work group where I have to have separate accounts on each system, I can join a domain. And when I join the domain and fill in that groovy.local here and then click OK, as long as the DNS points to that domain, I'll get prompted for a user credential that has privileges that will allow my computer by this name to be joined to the domain. And then it becomes a member server instead of a standalone server. That's significant because as soon as I do that, it takes my local administrator's account and it does something really special with it. So what I'd like to do is have one of you log into your system. I'm going to stop sharing And could I have one of you share your screen and log into your server one more time? No, this will only take a second. All you're doing is logging in and then referencing one item, and then we're done for the day.
I'm not by my computer right now, so I don't know if Luke will be able to share.
Luke, are you able to use remote desktop? Well, here's what I'd ask each of you to do. Let's handle it this way. If each of you, let me share my screen again. What I would like you to do for the first assignment of Module 5, I want you to log into your system. And once you log into your system, the management, the server manager will come up once you log in. And when it comes up in the tools option, you can select computer management. When you select computer management, this actually, let's open this. Computer management, this screen will open up. And inside computer management, you'll see users and groups like you do on my screen. And if you open up administrators, you will see embedded or listed in the members of the administrators group on the local machine, the domain admins group. So what are we saying? When a computer becomes a member of an Active Directory domain and a computer account is established, a trust relationship is implemented so that the domain administrator privileged account that's used to join the system to the domain takes over and embeds certain security groups, including the domain administrators group, within the local administrators group. This is how domain administrators can exercise privileges and permissions and inheritance. This is how the file system can effectively be extended by security group membership. And this is an important concept to understand. When you open up your computer management console and open up users and groups, what you'll see listed inside the administrator's account, inside the administrator's group, it'll say domain administrators. And what you'll do is capture a screenshot of that and submit it. And that's all you have to do to satisfy the criteria for the 5.1 assignment. Okay. Any questions before we stop today?